Hello everyone, this is Cunxi from University of Utah. I'm going to present my work on practical modeling of bandits in Boolean optimization. All the tools, benchmarks, and scripts can be found in this GitHub page. We recently saw many works on applying machine learning techniques in EDA domains. The main motivation is, although EDA is still an automation tool, but now it requires a lot more manual efforts for tuning the design flow to get a good performance. The main reason comes from the increasing complexity of the design and technology, but moreover, the big challenge comes from the large design space, slow evaluation, and the lack of predictability of existing EDA tools. Machine learning techniques are believed and have been used to improve the predictability in many applications, so is also believed to improve the predictability of the EDA tools, which can be used to accelerate the design space exploration process. So here is a list of limitations or challenges of traditional EDA flows. We are going to show a few motivating examples in the next few slides to show you the needs of addressing those limitations. So first, let's look at the example of evaluating technology mapping results at different design stage. So if we generate 5 different technology mapping solutions, and namely M1 to M5, and STA indicates that M3 is the best timing solution, but Git level evaluation shows that M1 is the best solution. And we know that STA analysis is more realistic than Git level, and this shows that the lack of predictability that is caused by the miscorrelated abstraction models in the EDA flows. So in this work, we focus on optimizing the synthesis flows that are basically a sequential decision-making problem. Here we first define what type of flow that we are targeting and how large the design space can grow. So here we first show a simple case that a permutation of 4 different transformations in ABC is basically the flow. If you don't know ABC, it is fine. Just remember each of these is individual transformation that can be applied to a design step by step to perform optimization. So each of the decision paths in this graph is basically one flow, and you can have 24 of these. However, the space is actually a factor of n, and it grows really fast if n increases. So the space can easily grow much faster than the previous example. So here we show that with only 3 transformations by repeat each of them twice. So we have 1 less transformation, but this actually goes up to 90 from 24. With this new assumption, the space can grow much faster than the previous assumption. So here we want to show how crucial it is to build the flow correctly. So 50K random flows are generated by random permutation and then are applied to 128-bit AES design. So first of all, we observe that different design flows can have very different performance, and moreover, we see that during random sampling, most of the design points are located in the bad performance area, that is the up right, because the delay and area distribution. And we can see it still are good flows, but it's hard to find with a random permutation. And your next question may be, how do this flow perform compared to default flows in ABC? Well, we run 3 of them, and we can see 3 of them are all in the versed QR area. However, I wouldn't say these are still the state of the art, because back then the flow was not really tuned by design space exploration, because at that time this was not really a problem that on the table. Following up the previous example, we took the same 50K random flows and applied to a different design, arithmetic unit. So we can see that distributions of the QR are very different compared to the AES, and more importantly, if we took 2 good design points in ARU, and they are actually pretty bad for AES. So we conclude that design flows should be developed carefully for specific design, and if you go more deeper, you have to develop the flow based on the design structure, the graph in this case. So let's summarize the limitations of previous work, and they are basically the motivations of this work. Offline training requires a lot of static dataset, which is very challenging and time-consuming to collect, which makes it not practical for large designs. A common limitation of ML-based approach is that they are limited to their training dataset. For example, if you have a model, it's trained on a dataset with timing as labels, the model cannot be used to predict area anymore unless you retrain this with a dataset with area as labels. So you have to basically retrain the entire system. The last one is about engineering. So if neural network or other complex ML models are used, deep learning frameworks such as TensorFlow, PyTorch will be used. However, integrating TensorFlow or PyTorch into existing EDA tools is very challenging, and naive integration can be done but will be very inefficient. To address those limitations, a domain-specific MAB modeling and algorithm are presented in this work. It does not require static dataset anymore and is flexible to almost all the QR metrics. We have explored a list of optimization problems in this work listed in the slides, and we also believe this is the first time algorithmic domain knowledge is leveraged in design space exploration for Boolean optimization. In addition, a significant amount of engineering efforts are applied here. We built Floaton in ABC framework and then integrated with VTR for FPGA design, YORSys, and other EDA tools. To further improve the performance in real-world applications, we utilize OpenMP package to accelerate the MAB exploration at the initialization stage. So no matter what kind of approaches you use, exploration always involves in sampling the design space. So what was the strategy people are using to sample a design flow? So in previous work, all the explorations are based on global sampling, which means that each exploration or each static data point is collected by sampling the entire search space. So the question is this a good strategy or something else can be done? So if it's not, what is missing? So to answer this question, we dig into the DAG-aware synthesis algorithms. So we took 6 different ABC transformations and applied them to I10 design. It's one of the default design ABC repository included. We exhaustively collected all the permutations of the as flows with only one appearance. So each of them appear once. And we observed that no matter which flow you choose, the earlier transformations always makes more impacts to the design optimization. So here shows, so how do we measure this? We basically measure how many nodes in the graph can be potentially optimized. That is basically showing here. So one, because all the graph-based synthesis algorithms are traversal-based, you have to trigger this if statement, and if it triggered this statement, if you apply this optimization once, right? So counting this kind of statement triggered is basically shows how much potential optimization you can apply to the design. And let's take an actual example on I10. So with only 2 transformations applied. So so we can see that the first flow compared to the second flow, the number of potential optimizations is always lower than the second if you look at rewrite, because balance is not doing much about optimization, right? So as a result, we observe more AIG node reductions as a final result. So to think at this as a high level, so the traditional sequential decision-making problem is mostly formulated as a Markov model. So however, the most important Markov property is not satisfied in logic synthesis. So because the probability of each event depends not only on the state that in the previous transformation, because it can depend on multiple steps, right? So as we saw in this example, once we made a bad decision, it could goes worse in the on the I10 example, right? So traditional sequential decision making approach will unlikely to work well. For example, reinforcement learning. If you take the action, each transformation step as an action. So we actually prove this statement by running this very simple example. So we create 2 disjoint space So one we start with rewrite, and the second one always start with balance. And for the rest, we use the same three transformations, and we just run enumerate all of them. So you can see that the second space is hopeless to win the first one, because the worst one in the first space is close to the best in the second. So this basically shows that if you make a bad decision at the beginning, and no matter how smart you are, you will never make it back in logic sense. Maybe it's not that strong argument, but let's see always in ABC synthesis flows. Now, based on this domain knowledge analysis and observations, we should agree on that a traditional Markov chain model is not ideal for synthesis flow exploration, because traditional MAB methods or other reinforcement methods, if you take each possible decision choice as an action, and in previous slides we proved that this is not a good strategy. And however, the concept of MAB algorithm can be used with a different bandit modeling for this problem. So MAB at the end is basically learning the optimal distributions of each bandit, and such that the agent can always take good action. So our approach, Floaton, basically used the same concept and state-of-the-art algorithm to learn the distribution. So I list some of these here. At the end we choose UCB, but for more information about MAB, you can find in the paper. So let's see how Floaton model the bandits. So based on our domain-specific knowledge on the DAG-based algorithms in the previous slides, we now define bandits as a sampler of an evenly partitioned design space. So specific in this example, so we pick three transformation candidates, and each of them can appear more than once, and we can define 9 bandits that evenly split the entire design space. So for example, here you can when you start with B, you have 3 different choices, right? So if you have start with RW, you also have 3 different choices. Then the action of each iteration will be generating one permutation or multiple permutation in P of A of T, right? So if agent select A of T, it was sampling some permutation in that space. So over the MAB exploration process, P will be updated based on the targeted QR results. So in this work, we choose mean of all the sampled flows. So if we do AIG minimization, we will do a mean of all the sampled flows in that space of their AIG reduction. So we observe that some of these bandits will be quickly eliminated in when you use ABC transformations, because the algorithm basically quickly learned that some of the bandit is hopeless to win the others. Just like the example we show in the balance versus reason computation, right? So initialization for exploration using MAB is very crucial. So we use the DAG-aware domain knowledge again. So P will be initialized by random sample a few times in all bandits. So what we did is we sample 5 times across all the bandits, and we count the number of potential optimization AIG nodes. So remember that if-else statement that can be triggered. So we count that as our initialization metric. So of course we normalize them, and then we will generate a probability for each of the bandits. And so because here we run a lot of things can be run in a parallel fashion. So OpenMP is actually used here to accelerate the initialization process. And so we discussed how design structure can affect the choice of flows using AES versus the ALU example, right? So based on that, we develop a multi-stage Floaton to further improve the performance. So the main reason to do that is that DAGs will be updated after Boolean transformations applied. So P cross all of them, so optimum P distribution will be changed after you apply those transformations because design changed. So the solution we develop here is we apply first part of the explored best flow like the first, let's see, first half or first quarter. So you can actually change that in our tool. And then FlowTune MAB will reinitialize these again. So P will be reinitialized and start again for the second half tuning. So these will give us the best performance. And we will going to show that in the result section. So this is the overview of our system. We built Ftune, FlowTune in ABC, so we can utilize the front end of ABC to take various of design formats to perform on different QR or different Boolean optimization tasks. So we have AIG optimization, we have technology mapping for both ABC, standard cell and PGA, and it's actually can be integrated with ADR completely because VTR use ABC for logic synthesis, and we also can optimize for CNF for SAT, and yeah, so more information can be found in the on the GitHub page. Let's look at the performance of FlowTune on various optimization problems. FlowTune is firstly validated on AIG minimization. Specifically, we choose 6 floating designs from VTR benchmark, and the bleed files are generated by running through the VTR high-level synthesis tool. The selected ABC transformations and evaluation functions are listed in the slides, and the baseline result is the best result collected with default ABC script and 2 of the previous ML-based exploration approach. One is static training based, and the other is reinforcement learning. Note that our baseline is not just running default ABC script once. We actually apply the default script many times. So specifically, we apply recent 25 times for all the design. So the result can be found in the paper, but I want to quickly show one of the example of Ftune versus default ABC script. So we can see that after 25 times, if you read a little bit, 25 times recent on this design, the number of AIG nodes is about 23,000. And Ftune report less than 20,000 AIG nodes after only a few iterations. So on the right side of the Ftune video, we can see that how OpenMP helping the FlowTune to maximize the load of CPUs. The CPU we used in this work has 40 core. So then we apply things to lot minimization. So in this case, we try to minimize 6 input lot mapping, the lot count. And yeah, so this is the same set, and we compare to different baselines, including the machine learning ones, same for the AIG one. And for SDA aware, we have 2 different setups. So you can do a quick setup, quick test with ABC, gate sizing, and static timing analysis. But you can also run this with Cadence, but you have to generate the Verilog and load into Genus to do the evaluation. And we can see that the tuning performance is pretty impressive, but except for our 1200, and so you can see there are some, yeah, so this design cannot be really optimized much using this. I think ABC cannot really optimize this design further. Yeah, so that one, this is the previous font for delay, and this is the area, and all of this can be found in the paper. So as I said, this can be applied to CNF or generation for SAT solving, and this is using exactly the same setup for AIG. So I just skip this, and we talk about that integration with other EDA tools, right? So this one we have integrated fully with VTR 8.0, and so you can see this is evaluation after the entire placement are running, and we can see we got 15% logic blocks reduction at the post PNR stage compared to the original VTR 8 flow, and the architecture and all this can be, everything can be reproduced on using our GitHub resource. Finally, I want to show you the result of integrating Ftune in Viva flow. We can see that in this example, the delay has been improved about 10%. And also we can see the difference in delay distribution. At this point, we don't really know how Viva optimizes the design, but My guess is that Vivado tried to move the delay to routing such that it can be further optimized by inserting buffers in the routing wires for larger designs. But again, I'm not sure what Vivado is doing exactly. I want to remind you guys again about how to access Floatune on GitHub. I also want to take this opportunity to thank all the team members in ABC, VTR, Yosis for making their code available. And please check out our GitHub page. Thank you.